Good afternoon, everyone. Welcome to this webinar entitled Acoustic Output Measurements for Therapeutic Ultrasound, presented by Dr. Samuel Howard. The AIUM is accredited by the ACCME. This webinar is designated for 1 AMA PRA Category 1 credit. By the conclusion of this webinar, participants should be able to understand the purpose and role of acoustic output measurements in characterizing, documenting, and regulating therapeutic ultrasound, understand the relation between acoustic output measurements and bioeffects, understand the types of instrumentation and protocols currently used for acoustic output measurements of therapeutic ultrasound, and understand how different measurement standards apply to different applications of therapeutic ultrasound. As an ACCME accredited provider, it is the AIUM's policy to ensure that the contents and quality of this activity are balanced, independent, objective, and scientifically rigorous. All individuals who are in a position to control the content of an educational activity are required to complete a disclosure form. All disclosures are reviewed by the AIUM, and any conflicts of interest are resolved or managed prior to an activity. Dr. Howard is employed by the Onda Corporation. AIUM staff have no disclosures. At the conclusion of the webinar, you will be able to access the CME test and evaluation located on the AIUM website. Participants who complete the post-test with a grade of 70% or higher will be awarded 1 CME credit. Credits for this webinar are approved for physicians, sonographers, and radiologic technologists. During today's presentation, if you have questions for the presenter, you may type them into the question box on the right side of the screen. You will be able to submit questions throughout the webinar, but the presenter will not begin answering until the end of the presentation, at which time he will answer as many questions as possible. A recording of this webinar will be available on the AIUM website. And now, we're pleased to present Dr. Samuel Howard.
Thank you, Darcy. I'm Sam Howard, and I will start off with this disclosure. I am employed at Onda Corporation, which produces and markets measurement equipment and measurement services for diagnostic and therapeutic ultrasound.
Sam, we
Yes?
cannot see the screen.
Oh.
There we go. Perfect.
Well, I'll start again. I'm Sam Howard. I'll just splash this disclosure up again. Again, I am employed at Onda, which markets measurement equipment and measurement services for diagnostic and therapeutic ultrasound. We'll again review the goals of this presentation, explain the role of acoustic output measurements in therapeutic ultrasound, describe some commonly used measurement approaches, and describe some of the challenges and limitations of current measurement approaches. Let's take a moment to review the role of acoustic output measurements. The role is to establish the acoustic conditions under which a treatment was or will be conducted to facilitate repeatability or regulatory compliance, for example, for publishing results, and to facilitate others repeating those results. Namely, if you are publishing results of a study on the use of therapeutic ultrasound, having the acoustic output measurements of that equipment specifies some of the conditions, some of the very important conditions of the study. Also, another usage is for certifying safety and effectiveness of devices or treatments. For example, for purposes of getting a CE mark or FDA approval, acoustic output measurements are a part of those processes. I want to take a moment to describe the role of standards in acoustic output measurements. Therapeutic ultrasound, and it's worth noting that therapeutic ultrasound is a developing field. There are many new techniques for acoustic output measurement under investigation for this application. Within this context, standards represent current consensus among national, for example, AIUM, or international, for example, IEC bodies that represent consensus for readily available objective measurements within this context. So basing the measurements on a standard technique eases the burden in justifying a technique for AOM, for example, in terms of reviewers. You can certainly have other measurement techniques, but when you refer to a standard, it's easier to justify, and you can just refer to that standard instead of having to explain the exact protocol that you use to characterize the acoustic output. Most regulatory groups, including the US FDA, are adopting IEC standards, which is why that's the focus of this presentation. So I'll take a moment just to describe what IEC standards are. IEC stands for International Electrotechnical Commission. This is a group that develops consensus standards through committees comprised of volunteer technical experts who are nominated by member countries' standards organizations. For example, in the US, there is the American National Standards Institute that basically designates experts who work with the IEC. And then such standards are adopted after a vote from the member countries. There are many different standards. There are many different standards for therapeutic ultrasound, and they're designed for different types of therapeutic ultrasound, and we'll be discussing that in a second. It's worth noting that each standard may reference multiple other standards in order to clearly define the acoustic output measurement. And it's also worth noting that generally the measurements are made in water because of water's wide availability and consistency of an acoustic medium. That isn't to say that other mediums couldn't become standardized in the future, but this is just what we have for most of these measurements today. I will take a moment now to describe the standard measurement equipment used, and this is done bearing in mind that we've had two recent seminars, one from Andrew Harrell, another one from Jim Gessert and Nick Ellens, describing much of this equipment, and those considerations still apply. So I will just briefly go over the equipment. First off is a hydrophone, which is supposed to be a point-like sensor that measures pressure at a position and measures a pressure waveform, so it's a function of time. As has been discussed previously, there are many different types of hydrophones that have been described in standards and then also previous webinars. So all those considerations such as spatial averaging, sensitivity, etc. Still apply. We will talk about some special considerations as we talk about the therapy realm, but we will not rehash all the details about hydrophones that have been talked about before. Similarly, there's a scanning system that the hydrophone is mounted in. Typically, this is used in order to position the hydrophone and map out a pressure distribution in space. Finally, as discussed previously, there's also a total acoustic power meter. This is a device that measures the total acoustic output power, typically in units of watts. Typically, a radiation force balance is used, as discussed previously in webinars and also this IEC standard. I will mention that there are other techniques based basically on the conversion of the power to heat, which can be measured as a rise in temperature in a calorimetric medium or as the change in buoyancy of a heat-absorbing object. But the basic take-home is that this is a device for measuring total acoustic output power. I will mention that there's an optional piece of equipment for rapid visualization of the field, particularly in the therapeutic realm. There's often concern about not just the place in the ultrasound field that gives the maximum output, but secondary maxima, which may be far away from features of the field such as side lobes. And because in these new standards, there is concern about those side lobes and a requirement to measure them, given that they can be far away from the beam axis. There is sometimes a desire to to first identify their location by doing a rapid, even if it's qualitative scan of the field, and follow that up with hydrophone measurements. And typical equipment for this are thermal imagers, phantoms, or Schlieren devices. I will take a moment now to review the relation between the parameters that are typically measured and bioeffects. On the left-hand side here, we see a schematic of a ultrasound waveform. This one is a pulsed waveform. It could also be much longer or even continuous. In this case, well, in any of the cases, the features that are of interest are particularly the negative pressure. I show a positive pressure here, but the negative pressure, as we'll discuss, is of particular interest. For a case of a pulse waveform, it has a duration, which has a precise definition that's been discussed earlier in terms of the rise time and fall time. In the case of a continuous wave, you could just average over one cycle. But the duration is particularly relevant for the intensity, which is approximated as the square of the pressure integrated and averaged over time. And again, if it's a very long cycle, you can typically take the average over a single cycle. These are the typical features measured in the waveform, and they're related to several different bioeffects. The first is typically cavitation, which is most directly related to this negative pressure. There are many other factors, as previously discussed, including the frequency, repetition rate, temperature, level of dissolved gases, distribution and size of any pre-existing bubbles. But in particular of interest, because it's the most direct factor, is the negative pressure in the waveform. The other bioeffect typically of concern is tissue heating. That increases with the intensity as well as with frequency. Again, there are other tissue properties that are important, the particular absorption, perfusion, conduction, etc. But in terms of the underlying waveforms, it's typically intensity that is measured in order to get a handle on potential for tissue heating. I should mention that there continues to be research on other potential bioeffects, for example, radiation force, but the current standards were derived with these effects in mind, that are the effects that are mentioned here. So given that, I wanted to briefly review what are the current IEC standards that cover acoustic output measurement. First of all, and most recent, we have standards for high-intensity therapeutic ultrasound, or HITU. I'll mention that HIFU is part of this. It's just that when we were developing the standards, we realized that there were some applications that did not involve focusing, which is what HIFU stands for. HIFU stands for high-intensity focused ultrasound. So to make this standard more inclusive, it was designated as HITU. And that was the theme of this standard, to try to make a general standard for some of these new therapies that are developing that were not designed for particular applications such as lithotripsy or physiotherapy, with particular high-intensity situations in mind. But since it comes up often, I wanted to list the other standards. We have, for example, the lithotripsy standard. This typically applies to the application of shock waves, for example, in the treatment of kidney stones. We have, for many decades, ultrasonic physiotherapy, which has been typically used for musculoskeletal applications, and is worth noting is these standards currently are designed for moderate intensities with an effective intensity of less than 3 watts per centimeter squared. Also, there are ultrasonic surgical instruments that are covered under a surgical instrument standard, and this is intended for vibrating tools which cut tissue due to the direct vibration of an ultrasonically very high frequency vibrating tool, such as in the treatment of cataracts. And the distinction there is, again, you're measuring or interested in properties of the tip vibration. Similarly for dental scalers. And finally, I decided to include the diagnostic standard in here, which has been talked about before in the context of diagnostic applications. But it is possible that you may have a therapeutic application that uses diagnostic equipment. And so I'm including it here, although it's worth noting that this standard was designed for equipment with diagnostic levels in mind. And although the IEC standards do not place limits, the US FDA does. So in practice, this standard has been used for equipment that fulfills the requirements that were talked about by Jim Gessert and Nick Ellens, namely a mechanical index less than 1.9 and a derated ISPTA of less than 720 milliwatts per centimeter squared. I'll also mention that these are the standards that refer to the applications. There are other standards listed in the notes below that are fundamental standards that talk about the properties of hydrophones and measuring equipment and things like that. That are more general, but these standards here are the ones that you would first look to when considering what your application falls under. I will also mention that the current field measurement standard, which we'll be discussing, which is 62556 for HITU, is a technical specification, which is basically a reflection of the consensus that the HITU field is developing rapidly, and we will revisit this. So it is designed as a temporary standard, as hopefully more as the field will develop and we'll have a more permanent guidance for how to make these measurements. I want to take a minute to discuss why are there so many standards. Well, each one applies to different applications, and although you could say that the underlying physics is the same, for example, for intensity, each one specifies the conditions for measuring intensity slightly differently. For example, in diagnostic, we have a derating factor that is developed for diagnostic imaging, and we have an interest in measuring the spatial peak temporal average there. For diagnostic. In physiotherapy, it refers to an effective intensity, which is an intensity averaged over the surface of the device. In HITU, as we'll discuss, there's another introduction of a new intensity parameter, which is SAL, which is another type of averaging that we'll discuss. And therefore, when you refer to an intensity, you have to define where it's measured, under what conditions, and if you refer to these specific parameters as defined according to a different standard, that's how you specify that. All this reflects different needs of the different applications and different approaches to the measurement challenges. So a common question is, how do I choose to follow a particular standard? Well, in the first case, if you have a fairly standard device that has clear precedence, then that makes it simple. For example, as I mentioned, physiotherapy has been in use for many decades. If you have, for example, an unfocused device in the range of 0.5 megahertz to 3 megahertz, as mentioned in the scopes of the standards, there is a clear justification for, and if it's lower than the output limits, 3 watts per centimeter squared, there's a clear justification for following that, given that it's so similar to many other devices. Alternatively, if it's not so clear, then you have option 2, which may require technical review of the available methods. That often requires a close familiarity of your application as well as the standards. Typically, these days, applied to emerging technologies, this second option results in applying these HITU standards, which is the focus of the remainder of this talk. And so I want to first set the stage by discussing what are the considerations behind the IEC HITU standards. The first is concern that high intensities or pressures could damage hydrophones. Although research is continuing on robust hydrophones that would not have this problem or would alleviate this concern, still none are completely impervious to the levels that could be achieved by some therapeutic ultrasound. Therefore, and also even more importantly, it's very hard to define definitive thresholds for when you should or shouldn't use a hydrophone. So therefore, measurements at these high pressures will take more guidance about how to check for applicability and also how to check for damage. That's under development, but it's not yet released as a standard. So therefore, the current standards had to deal with this as an issue. Secondly, measurements in water, the material still of choice, can give misleading results at high pressures. Water has very little attenuation compared with tissue, and consequently you can see high degrees of nonlinearity just due to the nonlinear stress and strain of the water. This can yield results that could confuse what you're predicting or measuring or interested in for tissue. And although there are mathematical modeling approaches to compensate for this, they too have not yet been adopted in a consensus standard. So that's another reason for being concerned about high pressure measurements with a hydrophone in particular. So how do the current HITU standards address these issues? Well, first of all, the hydrophone measurements are to be made at linear and safe pressures and intensities. And there are two ways of doing that. The first option is to reduce the electronic driving conditions of the HITU devices that are being driven to make the acoustic output measurements low everywhere in the field, so you can scan throughout the field without these concerns. The second option is if you have, in particular, a focus device, you can make measurements prefocally before the pressures and intensities become very high. Then what do you do? Well, that's the second bullet point. Some sort of mathematical extrapolation needs to be made to clinical driving conditions. In the case of that first option, where you made the hydrophone measurements at the low levels, well, you can scale to power measurements, which do not have these concerns, or at least not as much. It's much more feasible to make power measurements at the full output, and there is a procedure for scaling the hydrophone measurements at a low power output to the higher power output. The second option, where you made the prefocal measurements, can be supported by some advanced mathematical propagation techniques. It's essentially using techniques for solving partial differential equations to capture data that was taken in the prefocal plane and plug it into a partial differential equation type of solution that can predict what the pressure would be elsewhere in the field. And currently, this technique is standardized only for water and for linear propagation. That is, it does not include the nonlinearities that occur in water or potentially in tissue. But that is currently in the standards using these propagation techniques. So now I'm going to show an example of the use of these standards. I'll be talking about the option 1, where we make measurements at the focus using the linear scaling. In this particular case, there was an F#1 transducer with a 100 millimeter focus. It's capable of focal pressures of 60 megapascals with pulse average intensities of 10,000 watts per centimeter squared under a sort of typical 100 volt RMS drive. And that's what's shown here on the left. This was measured, as I said, for total output power at around 100 volts RMS with a radiation force balance, so we could get the total output power of around 100 watts in this case. Then the driving voltage was reduced to 17 volts RMS. That's basically around a 97% power reduction. Power measurements were repeated in order to help with the scaling, as we'll discuss later on. And PVDF hydrophone measurements were made with this and then scaled, as we'll discuss. This picture also shows the use of one of these robust fiber optic hydrophones, and one of these robust hydrophones, in this case a fiber optic hydrophone, so that we could actually compare the scaled measurements to some direct measurements that were performed at 98 volts RMS. I'll briefly also mention how you can be assured that you're in the linear regime. This is a somewhat complicated formula, but it's directly from the standards. Basically, if you measure certain parameters such as the pressure and the frequency and the distance and some of the focal properties of your source, you can estimate the degree of nonlinearity. And currently, the standards request this sigma parameter, which is the nonlinearity, to be less than 0.5. In terms of the scaling, this slide briefly mathematically describes the scaling. The scaling, of course, assumes that the field shape, the beam widths, the distribution does not change significantly from the low power measurements to the high power measurements. So that you can just scale everything according to these formulas. For example, on the right, the uppercase P denotes power as measured in the radiation force balance. PC is the power measured at the clinical level, around 104 watts. In this case, PQ represents power at the quasi-linear level, which was much smaller. And you scale the intensity that you measured at the low level by the ratio of these two power measurements to get the intensity at the clinical level. If you remember from the earlier slide where pressure squared was determined, where pressure squared determined intensity, you can see that the pressure should go as the square root of the power. So that's why this scaling approach is used here. Now, as I mentioned, this all assumes that the shape of the field, that the distribution of the field does not appreciably change. And in fact, it can in some cases. So as a better approximation, you can average out the change in the shape of the field by taking an average of the intensity along the 6 dB area of the beam, and that's where this ISAL concept comes in. Basically, you measure the power contained within the 6 dB area and divide by the area of the 6 dB area. And that's what this ISAL parameter is. And this just basically says that you can scale the 6 dB, the rate you can find the 6 dB power at the clinical level as from the ratio of the 6 dB to the full power at the clinical level. I see that there's actually a slight mistake in the subscripts here. This should be P6C and not P6Q, so my apologies for that. So I want to give some example results. The blue curve here shows the result from the hydrophone, which actually also agrees with simulations I should mention. So we have trust in this shape and form. Basically what you see is in reality in water, the waveform is distorted. You see a high amplitude positive pressure and the negative pressure is not so high, and you see On the positive end, it's narrow. This is what is called a weak shock wave, effectively. The red curve, which is the scaled result, is obviously far off in terms of the peak pressure. That's where it's most far off. The negative pressure is actually larger because of an effect called acoustic saturation. Similarly for ISPTA, that's also off by about 26%. But the ISAL parameter, which, as I said, involves averaging, was off by significantly less, by about 12%. I want to briefly discuss the other parameters that the standards ask you to report. First of all, there is the total ultrasonic power, that PC, an axial beam scan, basically to show how the temporal average intensity changes, is required also. Once you have that, you can also identify the position of the maximum, which is around there, and then the value at the maximum, which is the ISPTA. You can a planar scan, a cross-sectional scan taken at this position gives you the 6 dB beam area. Also shown here is basically the focal length, the 6 dB focal length of the axial scan at this position. We mentioned the ISAL, the rarefactional pressure peak, typically in these cases because of the linear approximation, it's at the same location as the ISPTA, and of course the acoustic working frequency. I will also mention that additional output is required off-axis. As I mentioned, there's concern about having collateral acoustic output away from the targeted area. So first of all, there is an effective intensity, which is just the average power divided by the area at the place where the beam enters the patient. There is also, as I mentioned, the possibility of side lobes, that is areas of high intensity away from the beam axis. That and its location are required to be mentioned, basically the second highest peak in the intensity field. Similarly, on the beam axis, there's a request for the prefocal peak, and that would be this, in this case, this little bump here. And as mentioned before, you can get this by hydrophone scanning the full 3D volume, but that can become somewhat time-consuming, so there are provisions that if you have a rapid visualization technique, such as Schlieren or thermal imaging, to identify candidate locations with that and follow up with a hydrophone measurement. Finally, there is some discussion about estimates for thermal bioeffects, and those are recommended in the standards, in particular the 2.2-62 standard. So we'll take a moment to discuss how you can relate intensity to temperature rise. The first bullet basically shows how the ultrasound can become a heat source. Basically, you have the intensity represented by the ITA at some position. If you know the acoustic absorption coefficient for the material, then you can calculate the energy deposition that the wave deposits as it propagates through the tissue. And that then becomes a heat source. Aficionados of heat conduction know that technically that should be then used in a full solution of the heat equation, but in many cases that can be approximated if you can neglect perfusion and conduction. If you have the heat source and the specific heat of the tissue, the temperature rise is given by this simple equation where tau is the exposure time. Now, as I mentioned, more accurate temperature estimates may be made with thermal modeling. In all cases, however, the specific heat and acoustic absorption properties, as well as the density, are needed for the tissue model that you have in mind. I'm going to show, for purposes of illustration, the type of data that you could try to get from this. This is for a phantom and some measurements that we did a while back. What we see on the left-hand side are images of this phantom that are showing wherever it's white, the phantom has achieved 65 degrees C. And overlaid on that are simulations based on acoustic data of where that 65-degree contour should be at different times. 10.5 seconds, 35 seconds, 50 seconds, and I apologize that's blocked away, but that was 72 seconds. And again, this is just designed to show thermal modeling, that you can use these approaches to estimate regions that have achieved a certain temperature. I will take a moment to discuss where we are. Clearly, there's room for improvement in the current standards, in particular dealing with the nonlinearities, dealing with tissue properties, being able to make measurements at high intensities, giving clear guidance for that. Nevertheless, these approximate results are obtainable, and at least these results provide a repeatable benchmark that should be readily achievable with existing methods. That benchmark how a system performs for purposes of repeatability. I'll mention what's in the works in terms of IEC standards, all targeted for completion date in 2018. First of all, this approach of doing mathematical modeling, including nonlinear modeling and extrapolating into tissue, is to be embodied in this IEC 62900 standard. The issue of how to work with robust hydrophones and make measurements at high pressures is underway, or it's being addressed in this 62937 standard that's underway. And finally, I will also mention that there is a standard that will extend the physiotherapy systems down, physiotherapy standards down to lower frequency, down to 20 kilohertz. And that is also underway. Since I know this webinar will be available, I decided to list in full the information about these standards that are also all available for purchase on the web. That concludes my presentation, and I thank you.
Dr. Howard, it looks like you have one question.
Let me make sure I see that. The question is, what standard covers ICE catheters that use ultrasound for imaging? Well, to my understanding, imaging is still diagnostic, and that is generally covered under the IEC 60601-2-37 diagnostic standards that we mentioned before. There may be some particular challenges because they're pushing up in frequency, but still the measurements, in my experience, are the same, and sometimes you have to make sure when you're measuring such a high frequency that you do a good engineering job at accounting for the uncertainties in those.
Any other questions from our audience? Oh, here we go. Whoops. I just lost that. All right, well, if you don't mind, I'm going to read it to you because I've lost it here. It says, how do
Okay.
acoustic output measurement for high frequency device over hydrophone calibration limit? Oh, how to do it. How to do the acoustic output measurement for high frequency device over hydrophone calibration limit.
I will interpret this question before answering it. I believe this refers to, as I mentioned, some of these high-frequency imaging devices that are sometimes getting close to 60 megahertz, which in terms of their center frequency, which is the current limit on what's currently available commercially for where you can get a calibration of a hydrophone. Now, this is basically referring to diagnostic equipment, not therapeutic equipment, but I'll give just from my personal experience what I've seen, which isn't necessarily good for everything. I've seen typically devices that have a center frequency that's in the 50 megahertz range. And what we typically do is we rely on the fact that we at least know what that sensitivity is at that center frequency of 50 megahertz. Now, technically, that can lead to very large uncertainties because there is significant bandwidth in the hydrophone signal that's above the calibration range. And there, typically, we just do our best to estimate what those uncertainties are by modeling, to estimate what might be the effect of that energy that has not been strictly and rigorously calibrated for on the uncertainties in the measurements. But with a center frequency that's still within range, technically we are following that standard which allows you to use that center frequency. The trick again is estimating how the hydrophone's bandwidth beyond the 60 megahertz range where you may have it calibrated will affect the results. And if you wish, since some of this is off of this therapeutic topic, I can go into more detail if you want to contact me about that, and I can just give our experience.
Okay,
Anything else?
There should be some other questions that I forwarded to you.
Yes, and you know, I'm having some, I'm trying to get it, let's see. Okay, does elastography have a standard? Not currently, and I know that this is a topic under a lot of discussion, especially for people doing elastography with acoustic radiation force imaging, where there is some feeling that perhaps going beyond the FDA limits on intensity may be desirable. I know this continues to be a topic of discussion, but I do not know of any standard as of yet. Another question, I will just read these aloud. Another question for, I will read the next question. Another question for acoustic output measurement for ultrasound imaging devices, ICE catheters. Do you know if the FDA is leaning away from using NEMA UD2 for ALM and towards IEC 60601-2-37? Well, I cannot speak for the FDA. I know that the NEMA standards are still recognized. However, I know that AIUM has been leaning away towards maintaining that standard, and FDA does recognize the 2-37. So I guess a personal viewpoint is I think in the long term, the IEC standards will be what encompasses these applications. I'm going to address the next question. Is there currently an approved standard that applies to devices that use frequencies below 0.5 megahertz. So this is an interesting point. I believe that technically the measurement standards do not give the essential safety standards, the ones in the 60601 series, do not list typically the frequency of scope. But the measurement standards, which say how you get the parameters that are required by those, such as an intensity or a pressure or whatnot, do have limitations of frequency in their scope because they describe measurement methods that have only been validated for a certain frequency range. So actually there is technically none of these measurement standards, for example, physiotherapy for diagnostic, that covers less than 0.5 megahertz. And that's why there is this effort underway, as I mentioned, particularly for physiotherapy, where there is some interest in lower frequency applications to extend the standard. I should mention that for many of these surgical instruments that apply direct cutting action to tissue, they cite some other hydrophone standards that apply way down to, I think, below kilohertz range. But then that is limited for the types of measurements that they do, which are very different from the typical types of field approaches where you're projecting an energy by wave propagation, or where it's believed that you're projecting the energy by wave propagation. So the short answer is this is under development, and the low frequency is something that you may need to stay tuned for. In the meantime, basically it is something that you have to interpret as best as you can. The next question is how to do acoustic output measurements for a high frequency device over hydrophone calibration limit. I think we discussed that question before, and I think I've gone through all the questions that are currently limited here or listed here.
We just had one more come in. Are you seeing it, Sam? What are the typical uncertainties in hydrophone measurements, and how are they handled in the IEC standards?
So it depends on the parameters. So the typical uncertainty in a hydrophone measurement is on the order of about 10% for pressure and 20% for intensity. And that is for the measurement at that particular point. What happens, and that's at the typical diagnostic levels. What happens is if you then try to go further and calculate uncertainties in some of these further derived parameters, such as, for example, if you try to use the intensity and integrate that over a plane for power, and other factors come into play. So typically the uncertainty can be higher, on the order of 25 or 30% for a power derived from hydrophone measurements. In terms of how this is dealt with in the IEC standards, again, it depends on the particular standard. And they each have their own guidance about what the uncertainties should be. Typically for diagnostic levels, many of the standards do basically say the uncertainties should be on the order of, like I said, 20% for some intensity-based parameters. But again, you'd have to look at the particular standard to see what guidance they have there and the particular conditions. Anything else?
We have one last question. Under what temperature will we cause damage to a transducer, say for a center frequency of 3 megahertz?
So again, this is highly dependent on the particular transducer, and I think there are two aspects here. we can take this as transducer or hydrophone. Transducer terminology is usually used to refer to the source, the HIFU device, and that is highly dependent on that particular construction. And I would I discuss that with the particular manufacturer. I can speak a little bit more about hydrophones, having some experience, typically manufacturers give some guidance about temperatures for hydrophones. I know this is very local, for us, but typically we recommend staying below 40 or 50 degrees Celsius for the temperature environment of a hydrophone. But again, this will be highly dependent on the particular design, and there are some designs that may withstand higher temperatures. And again, I don't think that that's a general number that anyone can give as a general number. It will depend on the particular design, both for the hydrophones and the transducers.
Okay, well, wonderful. I think that would wrap up. Thank you very much, Dr. Howard, and on behalf of the AIUM, our thanks to all of you who participated in today's webinar. Please remember to complete the post-test and the activity evaluation. We hope you enjoyed the presentation and will join us again for future webinars. So long, everybody.